So thanks for Professor Latex invitation. Today, my presentation is vibration energy harvesting design, analysis, and experiment. So I'm Shengxi Zhou, from School of Aeronautics, Northwestern Polytechnical University, Xi'an, China. And next July, there will be a conference focused on vibration and energy harvesting. So I invite you to come to Xi'an to take a look here. So the outline today, it may include the 6 parts. So firstly, I want to briefly introduce the mechanical energy harvesting. So now, we mainly focus on vibration energy harvesting, but for energy harvesting, it really have a very long history. So in the ancient period, the people, they translate the mechanical energy into mechanical energy. That means they use the ambient mechanical energy. For example, use to power the water wheel. So in a modern time, based on electromagnetic effect, we can translate the convert mechanical energy into electric energy. So that will be in a very big size. So recently, as new materials, low power electronics, as they develop very soon, so they need a small size power source. For example, we can base on some piezoelectric effect to design the vibration energy harvesting. So that is the so vibration energy harvesting. The harvester is really small compared with the electric one or the water wheel. So if we compare the size and the output power of the power generators, we can divide them. For example, for the 100 power station, so the output power is really high. We know it in the gigawatt level. So for the wind turbine, it may be in the megawatt. For the new one, this is the third picture of the first line. So this is a buoy based on the ocean view, so harvesting the energy from the ocean view. Its power is about from the hectowatt to the kilowatt. So for the solar panel, so it may have output power about hectowatt per square meters. For the vehicles, for example, so they have the damping shock absorber. So if we design it in energy harvester, so the level may be the 10 watt level. That means 20 watts or 70 watt. That's in this level. And this is a backpack. This one, the first picture of the second line. So it first appeared in the famous journal of science. So it's about the 4 watt. So as the size was decrease. So for example, for this one is a thermal energy harvesting. If it in a small size, that means maybe the 10 to 20 centimeters. So the output power may from the milliwatt to the watt. For the vibration energy harvester, it mainly focuses on the milliwatt level. So the middle picture of the second line. As the device, the size becomes smaller and smaller. So for the MEMS, so it's output power made from the microwave to the
perfect.
milliwatt. And for the nano scale, so its output power may be the nanowatt. So we focus on this size, yeah, the milliwatt level, the vibration energy
Hello,
height.
is
So the vibration energy height, it want to solve the energy supply problem for the sensors. So we know as many wireless sensors network, they are used in many different areas. So how to power them from power them for a long time. So traditionally we use the chemical battery, but they should be replaced when the power is used off. So how to harvest energy from ambient environment. So for the large scale, maybe the wind tunnel or the wind turbine or the solar energy harvest. So for the small size and very convenient one, maybe vibration energy harvester is a good one. So why we choose vibration energy harvester? So because firstly, vibration energy is very stable and it exists widely in environment. For example, in the human body, there are also a lot of the vibration energy for the heart. When we breathe, we have also when we speak, there are also a lot of vibration energy. For the vehicle, for the ship, for the airplane, they also have a lot of vibration energy. Sometimes the vibration is undesirable. For example, in the vehicle, in the airplane, so we can use the undesired vibration translate into the useful electric energy. So that may be interesting. And so the vibration energy hardening, the output power, it can meet with some low powered sensors, because now the size of sensors becomes smaller and smaller. So this picture and on the bottom of this page, this is compare with point. Also, we make the research on vibration energy hardening. It not only can use in the energy supply. So for energy supply, for human, so the heart, pacemaker, and also other medical equipment, it may have a potential way to power such device. And for other wireless sensors used in the structural health mounting or the other application, we can use the vibration energy harvester to power them. So also we can use the harvester to control the undesired vibration, because from the view of energy, if we reduce the vibration energy, that means if we translate some vibration energy into electric energy, that means the vibration energy will be decreased. So that is a way of passive vibration control. And for example, the airplane and the underwater vehicles. So besides this, some theoretical result or simulation result from this area also can be used in the signal processing. So energy, vibration energy conversion methods. So it mainly includes such as electromagnetic type, the tribal electric type, piezoelectric type, also other ones. So this is not limited to. So now I think a lot of researchers, they focus on piezoelectric one. And also for the device, so how to design a suitable device. So based on the piezoelectric effect, so I think many scholars, they design as a cantilever beam type. So for the linear one, it may have some limitation. For example, for the broadband and the broadband vibration, so it may not work so well. So, for example, the Professor Letic, Professor Artuk, they and also other guys also for the Dr. Maliji. So they designed a different type of the nonlinear energy characters to effectively harvest the broadband energy. So for me, I carry out this. I involve in energy harvesting either also for about I think 8 years. So the first work is to achieve broadband energy harvesting. So we designed the rotational magnetic coupled nonlinear energy harvester. That means so we can adjust the inclination angle of the external magnet to change the nonlinear dynamic characteristics of the harvester. And also based on some theories, we can get the final Gaussian equations. And also, so the FM means nonlinear magnetic force. I measure it in experiment and use a polynomial term to describe it. So this is the initial device in the lab. And if we change the angle, the inclination angle of magnetic external magnetics, so we found the magnetic force, they change regularly. So if we combine, that means we remove FM from the right side to the left side to combine with Kx. So that means the nonlinear equivalent restoring force will change as a change of inclination angle. And okay, so in simulation and in experiment, we also verify this. So from 0 degree to 90 degree, we found its dynamic response is quite different. So firstly, it can effectively work in 4 hertz, and in 90 degree, it can work in 22 hertz. That means we can change the inclination angle of external magnet to make the harvester have a very broadband characteristics. And also we see there are some multi-solution range. That means if we change the frequency sweep direction, so it may work the high energy orbit or the low energy orbit. So we can also verify it or realize it to change the initial conditions. So for the same excitation conditions, if we just change the initial condition, so it may realize the high energy orbit. That means the output voltage is higher. And also we can make perturbation in the excitation, and when also very short time, and it also can make the harvester jump from the low energy orbit to the high energy orbit. So this is the first work. So based on this design, we found in equipment the tristable and multi-stable harvesters. So this work firstly found this phenomena in the year of 2012, but the first population is 2014. So it takes a very long time for the first population of our tristable energy harvesting work. This the left structure, the left finger is a schematic of the tristable harvesters. So the 1, 2, 3, 4, 5. There are five equilibrium positions. So and 2 and 4 are unstable. That means we cannot realize it in experiment or physically. In experiments, we found the stable equilibrium positions. So that means the 1, 3, 5. This is the three pictures in the right side. So also we measured the nonlinear restoring force. So we can find that the restoring force have 0 point. That means 5 equilibrium positions. And in the potential energy function, we also found that the stable position, the stable equilibrium position stand for the potential while. This is such as A1, C1, E1. So the displacement according to the point 1, point 3, and the point 5. And also in simulation and in experiment, we found when the excitation condition change, so the vibration center may jump. It may jump from one stable position to another stable position. So we also make an initial comparison of bistable and tristable harvesters. So in the same physical space, the tristable harvester can be the potential while of the tristable energy harvester can design slower than the bistable one. So we can see the potential while of the bistable energy harvester is deeper. So that means the bistable one may need more energy to realize the large amplitude interval oscillation. We also get is nonlinear stiffness. So the black one is a linear one, and the blue one is tristable. The red one is bistable. So in simulation, we can find when the excitation level is low, the tristable harvester can realize interval oscillation, and the output voltage is higher than the bistable one. And when the excitation level increased, both the bistable and the tristable one can work well. That means the tristable energy harvester with slower potential while it may work better in the low level excitations. So this was verified in experiment. We can find the experiment result. Okay, so this harvester is a asymmetric one. So for a very general one, that means the general tristable harvester, it may be asymmetric. That means the potential while 1 and the potential while 3, they are not totally same. They may be different, and it will become a asymmetric tristable harvester. So we want to review the response characteristics of the general tristable harvester. We use the harmonic balance method to get its solution, analytical solution. So for its governing equations, for the piezoelectric one or electromagnetic one, so its governing equations may be like this. If the harvester is a asymmetric one, that means in its restoring force, it can have the K2 and K2 and K4 cannot be equal to 0 at the same time. And also we can find it has five equilibrium positions, and it can equalize at the equation at the bottom of this page. Okay, for the potential energy function, we become this. We assume that the displacement and the voltage has very slow varying coefficient. So that means x, y. So x have a difference, x have two difference. They can express like in this way, and we can get the final solutions. So we can solve the A0 and R. R means the amplitude of vibration, and V means the amplitude of voltage. The A0 means the vibration center. So we also get the Jacobian matrix to determine which solution is stable. So when the excitation level is very low, that means the vibration that means the vibration is introvile. That means it will be confined at one potential while. So if it confined at the middle stable equilibrium position, that means the A0 becomes 0 and the amplitude is very small. If it in the confined in stable equilibrium position 1, that means A0 like this one. The atom is the upper one, and if it becomes a 5, so this is a lower one. And we found it may have 7 solutions, and 4 of them are stable solutions. And we also use the basis of traction to verify the 4 stable position. So the blue one means this initial condition can lead to the interval oscillation. That means the output voltage is also large. So the color red, blue, and yellow, that means this initial condition respectively to the other 3 stable equilibrium position. That is the interval. Interval means confined to each of the potential while. Okay, so for the application of the mountain stable energy harvesters, so we want to use it to power the sensors in the airplane and the vehicle wear. So we know some sensors will be used to monitor the tail temperature, vibration, and the pressure. Okay, how to power them? So in the tire, so the working environment is totally different with the base one. So it have the base excitation, also have the rotational motion. So it's both of them harvest the energy from both base excitation and the rotational motion to power the sensors. So we designed a nonlinear harvesters. So the schematic diagram like this, the finger A and the finger B. And also we make the experimental device in the lab. So this is the design harvester. Okay, and also we compared the asymmetric tristable harvester and asymmetric tristable harvesters in the rotational motion. So we found in some cases the asymmetric tristable harvester may work better. So the red color one is the asymmetric tristable harvester. The blue one is the symmetric tristable harvester. So we can find from a wide range. So these two harvester, both of these two kind of harvester can work well. But however, the asymmetric one works better in a wider rotational speed range. Okay, we also use the method of participation to deduce the analytical solutions. Use pentastable one and get its dimensionless parameters and get the final comparison of solutions. So based on the analytical solutions, we can review the influence of excitation conditions and load resistance. So I think we familiar with this first picture. So along with the frequency, along with the change of excitation frequency, so the harvester may have the multi-stable range. So this is a multi-stable range, and also as the change of excitation amplitude. But the interesting one is as the change of the load resistance. So we can find the load resistance also have an influence of its its response displacement. So, but not so obvious as power. Also, for the damping, for the electromagnetic coupling coefficient. So not the higher not so electromagnetic coupling coefficient is not large, is not too large for biased one. So the a biased one, it will associate with excitation frequency. So we can find when the frequency is different, so the biased electromagnetic coupling coefficient is also different. So this is for capacitance, and this is as the excitation condition change the stable, the unstable region. It also can change. So for the potential wild depths, we make research focus on the different multi-stable energy harvesters. So if we confine the distance between the two outside stable equilibrium positions as the same, so as the number of equilibrium position increase, so the potential wild depth will decrease. So that means as equilibrium position increase, the energy orbit will also decrease. It can harvest efficient harvest energy in a wider frequency range, but the output power may be lower. So this is from N is 1, N is 2, N is 3, N is 4. As it changes, we get the simulation. This is output power. And also we use experiment to verify it, but we use just the tristable one. So the tristable one, so the TEH1, that means tristable 1, tristable 2, tristable 3. So the tristable 2, its potential wild is the source. So that means it can make the interwire oscillation easier than the other two. Okay, so for the nonlinear energy harvester, we know it have different orbit. So how to make the harvester oscillate at the high energy orbit in the multiple solution range? It is a question. So we designed the impact-induced method. That means we make the impact at the end of the harvester. So to change its initial conditions to make it vibrate at a different orbit. So we just make a very primary investigation of the impact-induced method, and also we make 3 assumptions. Okay, so this is a simulation. So in simulation, we just change the initial velocity. So if we change the initial velocity and keep the initial displacement and the initial voltage 0, and we can find. So for the different initial velocity, the harvester may work in the high orbit or the low orbit. So make the impact. So when the harvester work, make the impact in the middle equilibrium position. So that means it can change the velocity of the harvester. And also we make the experiment to verify this. So here is the input. So impact. So before the impact, the harvester work in the low orbit, the output voltage is also lower. So after an impact, so the harvester may be induced at the high energy orbit. Sometimes the impact is very difficult. So opposite the suitable impact are very difficult. So sometimes we make 2 impacts. So for the second picture. Okay, so the second, the third column of the fingers. So we found The red color means the heart with 0 initial conditions, and the excitation frequency is constant. So we found the bistable and tristable not work very well for the constant excitation frequency. So if we give them the suitable impact, so the output power will become the blue one. That means the output power error will be increased, and the energy harvesting efficiency will be increased. So this is so for the next one is uncertain analysis of nonlinear energy harvesters. So we know the nonlinear energy harvesters, they are very sensitive to the excitation conditions, and also very sensitive to its parameters. So we can find it from these pictures. So therefore, we make the uncertain analysis. So processing, manufacturing a sample, environmental influence, and model hypothesis. This all will make the harvest become uncertain. So in order to review the influence mechanism of the excitation conditions on energy harvesting performance, so we make the uncertain analysis. So for the classical uncertain method, this is the classical interval excitation. And we use the second order Taylor expression to analyze it. So this is a process of make the boundaries of the function. So this equation is very important to find its boundaries. And we also compare the lower and upper bound of the function, so we can find, and also we make the comparison with a Monte Carlo simulation with 10,000 times. So this is improved interval extension based on second order Taylor series, and this is Monte Carlo simulation. So we found the error between the presented method with Monte Carlo simulation. So the error is very small. So here, the red line is from the presented method. So the blue one is Monte Carlo simulation. So we found that so the boundary is very close to the Monte Carlo simulation. And for the different excitation conditions. Okay, so besides the nonlinear energy harvesters, we also make some new design. This is a flexible longitudinal zigzag structure. So this structure is to effectively harvest multi-directional time-varying vibration energy in small-size device. So this structure is very different with traditional zigzag structure, because the blue beam is synchronous direction is in z direction. That means the blue beam, they will vibrate in z direction, and the red one they will vibrate in x direction. So we can make the size smaller. So this is a derivative process of the flexible zigzag structure. So first is a very long beam. So we bend it 90 degree. So become the L beam. And the L beam, if we bend it again 90 degree, it will become a U beam. And bend it again and zigzag. So this is a derivative process of the zigzag structure. So this is assumed bending moment couple and the reference frame. And we make the very detailed Gaussian equations. So we assume the general Gaussian equation for free vibration of each segment. That means each beam in this structure. And the model shape of two kind of beams. That means the blue one we make it in one kind of beams, and the red one in another type. So we use the different model shape to describe them. And also we assume the boundary conditions include the continuous displacement, continuous angle, continuous bending moment, and continuous steering force. And we make the normalization of the mass. So we compared it with finite element method. This is result from ANSYS. So I would like to explain what is ideal zigzag structure. The ideal zigzag structure means the joint error is very small. In this picture, that means the black one between the blue beam and red beam, there is a joint error. So if it's very small, we call it the ideal one. So the third model with the finite element method, so the error is very small. So we can check. So for the different model and the different lengths. For the general one means the joint error is not ideal, is not very small. So it may be very large. So like this picture. This is with large joint blocks. So we make the new boundary conditions. So we most focus on the bending moment and the shear force, and also make the normalization of the mass. So this is impairment. So we found the joint mass is very large. So that make that very difficult to get the exact model. Okay, we also compare the finite element method with result with the impairment. We also found a very large error. So this error caused by the measurement, because the size of the joint mass block and the size of the beam, we cannot measure it very exactly. So that means that makes the error appear between an element analysis with impairment. And also our model has the error with the impairment, both impairment and finite element method. So we know the error is caused by the big joint mass block. So if we reduce the joint block mass reduce its size, we found the error between the model, the certain model with the finite element method, it will become very small. Okay, so we also get the power function of frequency response function. So for different, this is for n is 4. That means 2 blue beam and 2 red beam. This is n is 5. So impairment result with a certain model, we compare it, and we put totally 8 piezoelectric patch. So here, like this picture. So we can predict the output of the each piezo material, and also if we change the excitation angle, so this harvest also can sometimes efficiently harvest the energy. Okay, the next work is for flow-induced vibration energy harvesting. I think next week, Dr. Junlei Wang, he also will present some result about this. So this is also cooperated with him and also Daniel. So this is a vortex. So if we remove the wire attachment from the bluff body, so it is a vortex induced. It will make the vortex induced vibration. However, if we put the Y-shaped attachment, it will become a galloping vibration. Okay, the second picture is we designed magnetic coupled flutter-based energy harvester. So we put the magnet on the end of the piezoelectric beam of the flat-based harvester, and also put 2 external magnet to make the magnetic couple one. So this is the analysis from the CFD, computational fluid dynamics. So for the vortex vibration, so its vibration amplitude is not as large as galloping. So this is the result. So for this design, we can easily translate the vortex-induced vibration into galloping and flexibly harvest the energy. This is impairments. And this is magnetic coupled flutter-based energy harvesting. So the blue one is okay. So the red one is the magnetic coupled. So I make an error. Okay, the red one is nonlinear magnetic coupled flutter energy harvester. So the blue one is no magnet. So we found the cut in wind speed of the magnetic coupled one is lower than the traditional flutter energy harvester. That means if we put the magnetic coupling in the flutter-based energy harvester, so it can efficiently harvest harvest energy from low wind speed. Okay, so based on above research and also we make a very long review. it is 56 pages, and we analyze the research structures, the challenges in issue, and the new research directions of piezo energy harvesters. So it published 2 years ago in the Journal of Geology, the Cell Prize. So in my opinion, so vibration energy harvesting has a great application potential, and it was researching. So vibration energy harvesting belongs to grid energy, and it will play an increasingly important role in energy field, especially in micro energy field. And the vibration energy harvesting can be also used in biology, vibration control and sensing. Vibration energy harvesting has a very huge potential application market, such as low-powered electronics, medical treatment, and watches. Here, I want to thanks to my collaborators, for example, such as Professor Li Teik, Professor Dan Yimen, Professor Lei Zuo, Professor Jun Yicao, and Professor Daniel Yusenko, Professor Michael Lala, Professor Nakino, Professor Ertuk, and Dr. Junlei Wang, and Dr. Dongmei Huang. So Dr. Dongmei Huang is my postdoc. So about research also about research have a collaboration with these famous scholars. Okay. And special thanks to Professor Li Teik and Peter and other colleagues from Lublin University of Technology for organizing this energy harvesting seminar, and thanks to the program of Polish Ministry of Science and Higher Education under Project Dialog. Okay, thank you very much.
Okay, thank you very much for this interesting Shengxi Zhou, Professor Shengxi Zhou will answer some questions. We still have some time, so we can discuss in such way. I think that this would be the best way to ask the questions through the chat. Yes. Okay. So I have a comment. The comment is about this. You discussed the system with this was like a magnetic multi-well piezomagnetic multi-well system, which was induced by impacts, and then you suggested that sometimes you apply several impacts, but this is quite difficult problem, because in these impacts you have to remember that there are many solutions in such a system, multi-well system. So you can switch from one to the other solution, but you can also destroy some good response. So one should probably observe the system and make impact if the system is working, if the output is very small. Yeah, this is. Have you tried some to identify the solution which you have before the impact?
You mean the solution of
or response, yeah, or response. You have some response and you apply some impact, but this depending on the response you have and how to distinguish different responses, because you could have several different solutions or responses.
Yeah. So this is very good question. So thanks, Professor Leitig. Yeah. So it's sometimes it's very difficult to identify the solution. So put the impact. So I just make a very pre-sample investigations on the impact-induced method, and the assumptions are very simple. And if we want to exactly control the impact method, so first we should have a very good model of the harvest and also the model for include the impact, and then we can find which conditions is suitable, and also make a very exact control to the impact. So if we realize it in the real world, it will be very difficult.
Okay, and now maybe there are some questions which appeared on the chat. Maybe you can concentrate. So thank you very much for your answer, and you can now look to the chat and try to answer the questions.
Yeah. Okay. I see so Dr. Malaji's questions: how to take care of the flogger in the large amplitude tristable harvester? Yeah, so this is a good question. So it mainly focuses on the material and the structure itself. So for the large amplitude vibration, so for a long period, sometimes it may destroy the structure. But how to say if the amplitude is not too large? So for example, here I can show you. Okay, so for this picture, the magnetic coupled flutter-based energy harvester. So the magnet in one side, it can put the nonlinear restoring force to the harvester, and on the other side, it also can confine the harvester, make the vibration not too large. So for the general one, for the general tristable harvester, so if we use the harvester in the real world, that means not only in the lab. So we also should consider this question, and also consider the material, the structure, and the amplitude. So and also define maximum amplitude of the harvester. So also, if the vibration is too large, the piezoelectric material also will break. Okay, thank you, Dr. Malaji. And another question is from Liu. So what kind of broadband excitation do you consider? Have you also observed the result from? Okay, thank you for your question. So in the real world, the broadband excitation, it will have the rod excitation and harmonic excitation. So in my current work, so most experiments focus on the harmonic excitation. So broad bands means the frequency range of excitation is very broad. For example, from 1 Hertz to 25 Hertz. So we in the past experiment, we consider this, and also, like you said, the random excitation also broadband, and I didn't do the experiment from for under random excitation. So broadband, it can divide into two kind of different excitations. The one is harmonic. It will have a very broadband frequency range, and another one is random. So for the harmonic one, for example, the rotational motion, it also the harmonic, and also the other applications such as machine, and it have a periodic response, and also the frequency of the periodic motion is not a constant. It may be the broadband. So another one is the random one. The random one, for example, in the airplane, it have a very broadband random excitation, and and also for other for the water. Sometimes the water wave also have the random excitation. So currently, my research focus on harmonic one. Okay, so
okay, thank you for your answer. And yes, I was just wondering whether you have also some experimental results on the broadband random excitation, and it's I think worth to also look into that if one considers energy harvesting. Thank you.
Okay, thank you for your question. I think in the future I can try. Okay, I can try some random excitation for energy harvesting. Okay, this is from the Kasim. So thank you. Okay, have you analyzed the evolution of basins for multi-stable vibration energy harvesting with respect to? Okay. I didn't make the analysis of the with the impact. So how to see here? I can explain here. And okay, so for the impact, I assume the impact changed the initial velocity. So when the beam when it vibrates at when it go to the middle stable equilibrium middle equilibrium position. So here we make the impact to change its initial velocity. Okay, so that means I make the simulation like this. So I care more about the initial velocity. So I just consider the initial displacement at 0. So because here is 0, and I just change the velocity and found this picture. Okay, so if you want to, how to say, to make the basis of attraction with impact, if you want to make the impact, that's also okay. You can assume the impact change with kind of its condition. So if you assume the impact not only change the velocity, but also change the displacement. So that means you can drive this kind of basis of attraction. So physically, the impact change the motion of the harvester, but in mathematically it changes the displacement or velocity. So you can consider, if you consider impact change the displacement and velocity, you can use this kind of Bayesian of attraction. If you consider impact just change the velocity, so I think this picture is enough here. Here, this picture is enough. But if you, how to say, want to make a very, very exact impact associated with this very detailed process, I think we should first make a very, very complex but exact model of the impact. So for the impact process, I just make a very simple assumption. Okay, is it clear? So Dr. Kasim?
Thank you very much for the response. I was just wondering about the robustness of this method. How robust is it in terms of tuning the basis of attraction with the impact?
Okay, so in the experiment, just with a very simple experiment, I use a stick to impact the free end of the harvester, not with control. That's the, how to say, qualitatively make the experiment.
Yeah, maybe it can be future work to tune the basis of attraction in such a way that you reach systematically the upper branch.
Yeah. Thank you for your suggestion.
You're welcome.
So,
thank you for this talk. Yes. So I think that this is very, it was very nice presentation, and I would like also to give one more comment. For example, to the zigzag structure, I think that this zigzag structure can be also extended to a kind of metastructure, because this is very, this kind of structure is very periodic. So if you can have, if you have enough large structure, then you can think that this is like multi-body system with periodicity, and this is like metastructure. So the periodicity could give some more effects on this structure, and I think that this could be useful to extend this study in this direction of metastructure.
Okay, thank you very much for these valuable suggestions. Yeah, maybe we can try in the future. Yeah, it will be very interesting.
Okay, so I think that if there are no other questions, we can close this seminar. And I'm telling that we don't have still the speaker for the next week, but in 2 weeks, 8th of July, we have the speaker, Dr. Junlei Wang from New Zealand, and this is a slightly different time, but we will send you the information, and I sent some invitation to Alper Ertig for the next week, but we don't have the response. Yeah, but
just a moment, Gregor. Hello.
Yeah. Yes. Yes.
I am informed that you invited Slim Neifer for next week, and I know that he will answer positively.
Okay. So we have a speaker. So I think that for the next week it would be Slim from Germany. So I haven't checked properly the mails and I haven't noticed that he responded. But this is very good information. So we can suggest Slim for the next week. So this is 1st of July, yeah. And for the 8th of July we have Junlei Wang, but this is in 2 weeks and slightly different time. So the Slim would be next week at the same time, 4 o'clock.
It will be on magneto-electric converters and how to make modeling and design of the converters.
Okay, very well, very well. Thank you very much. Yeah. So we will send information to everybody about this meeting. So thank you, Alpha, for
many thanks also. Yeah.
for us. Yeah. Okay. So thank you very much for all the people who participated and also for to the speaker. And I think that we can also in future we can think about some panel discussions, but we want to start with several lectures, some focused on some problems, just to have some idea what is the topic of interest of our participants, and later maybe we can think about some panel discussions, but this is probably in some next month if we can continue this kind of seminars. So thank you once again for coming here and for participating. Yeah. So see you.